Hey guys, welcome back. So we're on to one of our last sections for chemistry. Yes, thank goodness, right? So a couple things again, just as a quick reminder why we're doing all of these before you're like, we signed up for a human anatomy class. Why are we learning so much chemistry? Remember, everything that we do in human anatomy as far as the molecular level has a lot of chemistry to do with it. For example, we're going straight into immune system, right? And the interactions between bonds and attractions and all that is a large portion, especially when we get into proteins, because this is where the immunoglobulins are going to be created. How do they interact? How do you denature foreign materials? So it's a lot more than just chemistry. Okay, so let's get started, and we're going to do the most important one, proteins. Okay, so whatever you think molecules do, proteins are pretty much the key. They do everything. They build your body, they build your hair, they're your cells, they're your defense, they're your transportation, they're your communication. They break down things, they make things faster, they do everything. But proteins by themselves, Proteins by themselves are just nothing. They're just like amino acids. So amino acids are, I like to just explain to them as kind of like bricks, right? They're individual small pieces by themselves are nothing. However, when you put these bricks into a special formation, you build beautiful structures. You can build buildings, houses, cathedrals, all from the same brick, right? So amino acids are going to be more complex. You learned about it in basic biology, so I really don't want to go into it because there's so much about transcription and translation. For this class, simplicity's sake, just imagine amino acids as bricks to building your body. We're going to see how the bricks are organized because we need to know how to disorganize them, okay? Alright, so normally, this is you. We have your blood cells. And now I'm going to draw down over here at the bottom because drawing red on red, as you can see, doesn't really work, alright? But a red blood cell normally has 4 hemigroups in it, which will carry one oxygen molecule each. So essentially, your red blood cells can carry about 4 oxygen molecules. Okay, that's nice. So now what? Okay, so this is really, really good if you are normal. However, there is a hereditary disorder right over here, right? And this disorder is going to be called sickle cell anemia. This is just showing you how important your bricks are. If you just have one brick off, one amino acid, right, off, everything changes. Everything is going to be out of whack. And so we need to know how come it's such a dramatic change, as well as what is the significance for it in our bodies. To do that, we need to know its structure and how it works. So how are amino acids put together into the form of a protein? Well, there's 4 structures that it can make. The first one is its primary structure, secondary, tertiary, and quaternary structure. Okay, it sounds very, very complicated. If you want to make it this way, this is the simplest form, right? This is very simple here. Okay, what it is, each one of these are just amino acids formed in a straight line connecting to each other. No shape, no direction, just at its straightest form. So if I wanted to draw it, I could easily just draw it as a straight line. There, I'm done. And on this line is just amino acids connected together. Okay, simple, right? So if I had to say, hey, draw me a primary structure, you draw a straight line, next answer, right? Pretty easy. Okay, secondary structure is a little bit more complicated. Secondary structure is kind of like the picture I showed you earlier. This is called an alpha helix, so it makes this helical shape. Okay, so if you take a look at this, this picture here, this is a helix, right? Kind of looks familiar like DNA, right? So this is a helical shape. It also can make what they call beta sheets, which is in a zigzag formation, right? So if I had to draw it, I can draw swirls, or I would have to draw zigzags. Now, the question is, well, how did I get that shape in the first place? How come it's not a straight line? Why is it swirling? Why is it zigzagging? Well, that actually talks about the hydrogen bonds, and remember they're indicated as dots, that are in the alpha or beta sheet. Okay, the alpha helix or beta sheet. That's controlling it. Remember, when we use the water molecules, water either loves Hydrogen loves oxygen but hates hydrogen. So when certain molecules, pluses and minuses, come together, they'll either start pulling toward each other, or more importantly for the beta sheets, repelling each other. Okay. Now I'm going to skip this tertiary one because I do not like this picture, but this is one of the best pictures I could find because I don't like this picture, so I'm going to show you a better picture. So bear with me just a second. This is a tertiary structure. Okay. Now remember I said, hey, whenever there is an ionic bond, it will tell you there's the one and only ionic bond we're going to be talking about. Okay, so let me explain this. Now I always remember this as some sort of magic lasso. Right now the lasso's coming this way. I always remembered it, oops, let me try that again, right, as something like this, like a lasso. So you want to picture the guy swinging it around, right? So up in here, just like in there, there's an ionic bond, just like over here, right? There's an ionic bond on the top that's keeping the lasso open, but holding its shape. This bend here, right? This push, this are the hydrophobic interactions. So what they're doing is they're keeping each other apart. However, this wants to be pulled towards here, and that's what this is, right? This here is going to be this is the hydrophobic interactions. There's going to be the attraction over here, and that's what this little closeness over here. So it's pushing it open as it's trying to pull down. What I'm showing you here, this are the disulfide bridge. Okay, the disulfide bridge or a disulfide linkage is going to be simply two sulfurs or di, right, connecting it together, and that's going to be the base. Okay, so now what was that loop holding it together? Why is it coming this way? It's because, again, hydrophobic interactions, and this is the hydrogen bond trying to get there, right? And it's being pulled down this way, and the ionic bond is going to be the one at the lasso. That's why I like that picture more so than this one, because you can see this doesn't really show it as much, right? In fact, barely shows it at all. So I wanted to show you that. Now, the quaternary structure is going to be the culmination of these guys combined together, right? I like to try to think about it as, like, you know, if I got these swirls and I got the zigzags and I got my magic lasso and I can interact them with another one, and because what happens is proteins interact with multiple protein levels. Okay, they're not just one. For example, this picture here, you notice there's a blue one and then there's a red one. There are two separate proteins working together to make a bigger one. I told you in the red blood cell, right, that there is 4 heme groups intertwined in there, which is true. There's no way I can draw it. It's very complex. But there's 4 of them. So you see a blue and a red. Imagine if there was a green and a yellow that were mixed in together and it formed one of them, and that would be how they work together. Okay? So now, why is it important? Well, one particular reason specifically for the immune system is your enzymatic reactions, enzymes. Enzymes form a massive role with immune system, digestive system, you name it. It's a huge deal. So we have to know how this works, okay? So I'm going to be doing briefly a summary of a chemical reaction, okay? So how enzymes work. Here's an example of multiple pictures. You see the yellow, the green, like the yellow, green, blue, teal, right? All that. But they're all working together to form one enzyme, okay? Okay, so how do they work? So here, just a summary, but I want to tell you more so how it works. And again, I like explaining it a little differently, okay? A catalyst is an enzyme. And all enzymes are catalysts. Not all catalysts are enzymes. English. Hey, like, what? What are you talking about? Think about soda, okay? An enzyme is a Coke, and catalyst is a soda. All Cokes are soda, agreed? Doesn't matter what Coke you get, cherry Coke, Diet Coke, Coke One, whatever, right? They're all sodas. But are all sodas a Coke? No, because you have Sprite, Dr. Pepper, root beer, you have a whole bunch of different ones, okay? Because catalysts have a definition and overarch everything by that definition, including an enzyme. For example, a catalyst will change the rate of reaction, which we're going to be focusing on. They are not consumed in the reaction, and they lower the activation energy for the reaction. Okay, easy to reach the transition state. Now, these are all definitions, right? And sometimes you're like, if you haven't had chemistry before, it's a little confusing. So, let's just do this in a nice, easy way. Okay, so right now, all right, you get to see my awesome drawings. You got a bicycle, right? You got to go up a hill, right? You put energy into it. You're biking, right? You're biking really, really hard. You put in energy, right? Okay, good. I'm just gonna make up a number and make it easy. Let's just say whatever, 100 energy. Okay. Now your bike. Oops. Of course, the thing erases. So right, get your bicycle going up 100. Right? You have now stored energy. Okay? So now what happens? You sit at the top of this hill. You're not doing anything. It requires a push, doesn't it? A small bit of energy to start you up, to get this bicycle going, and then you can freely go down this hill, right? And what happens is that energy is going to be released, and you're going to know it as like speed. Okay? So this is just basics of kinetic and potential energy we learned back in middle school. Okay, so why is that important to us? Okay, well, energy is going to be in the form of bonds. Okay, so for example, I'm going to leave this bicycle here. We have carbon and a carbon, and we need to make this very, very strong covalent bond. Okay, now to put it together, you have to put in energy to put it together, right? Good. You have to put a ton of energy to make this work. Okay, so you put a lot of energy in, right? You get a ton of energy. You put it in there. Boom. Now we connect them. Okay, great. Now that energy is stored in the form of a bond. So what do you have to do to get this energy out? Right? You have to break this bond, which is that starting energy you need, right? You have to do something to break it. And what happens once you break it? All that energy is then released. It's like you having lunch and eating a Snickers bar, isn't it? Like chewing on some sugar. Okay, so this process is about understanding chemical reactions, right? So a chemical reaction speeds and changes its form. We have its reactants and its products, okay? The reactants is stuff you're going to start with. The product is the stuff you're going to end with. Again, we're going to simplify it versus keeping it very in advance, just for conversation's sake. Okay, so we got our reactants. Okay, just like I showed you earlier, right? We got it over here. You got to put some energy in. Once you put in enough of this energy here, you reach a point called the transition state. Now, what does this initial energy needed to get to this transition state? Okay, once you get to this transition state, it will change its form, and then it will go in through a new reaction, and this is going to be the product. Okay, now it's going to have these deltas and all that. I'll explain these in a moment. Okay, but this is the process of how energy is. Now, energy can be stored, which is what I told you earlier with the bicycle, right? If you want to think about it this way, here's my little bicycle. Boom. Right? I am putting energy in. I'm at the bottom of this hill, right? I got the bicycle here. I'm coming up this hill. And I'm all the way at the top. I got up to the top of this hill. Bam, I'm ready. Right? I'm good. So I stored all that energy like I did earlier, right? And this is called an energy absorbing, right? It's going to be putting energy into your system. I could now erase this, right? I could do this with the sun, right? I have the sun. Now what? Sunlight shoots down, and what does it do? You find a plant, all right? This is my ugly plant here. What does it do? It absorbs the energy. It uses the energy to make a product called sugar. Now we got sugar. We're holding it. It is stored, as you said earlier when we learned about sugar. It is just stored energy, isn't it? Okay. So then what happens? All right. We have all of that stored energy, right? You get that stored energy, but you need to put energy in to get it out. It's just like the bicycle on the hill, right? Just because you're on the hill, you don't magically go. You have to either put energy into it. Somebody pushes your bicycle, you have to pedal it, and then you go. You have to put energy into that system. That energy that's required to start it is called the activation energy. Okay? That's the energy necessary to get you going. I like to think about it like weightlifting, right? You got your rack, you got 100 pounds. Remember, easy numbers, right? 100 pounds. You could push 99 pounds of strength all day. It ain't gonna move, right? You have to push at least that number, if not more, to make that weight move, okay? All right, so a couple things I want to go over. An enzyme, as well as a catalyst, affect the speed of the reaction. It does not affect the overall energy. Now, this one's a little confusing, so let me explain it. Imagine I have two friends, okay? I got friend A and friend B, okay? This person over here, we're both going to a barbecue, okay? We're both, let's just say we're tailgating at the football game. This person's gonna light up their charcoal. This person lights up their charcoal with lighter fluid, okay? Who's faster? Of course, the lighter fluid guy, he's gonna be faster, isn't he? Then I'm gonna ask you the question, whose fire's hotter? And a lot of times people will say the lighter fluid, but what happens is the lighter fluid, just like the catalyst or the enzyme, it helps it reach its state faster, but isn't the end goal still the flame, right? Still cooking and burning of the charcoal. So they both have the same amount of energy released. You're just putting energy in it to get it started at a faster rate, okay? So this is important. So now we're gonna get a few names on this. We got this thing called a substrate, okay? And that's anything an enzyme happens to be working on, okay? So, for example, like we have maltose, it's a form of sugar. You could break it down with maltase. You guys heard this one before, lactose. I am lactose intolerant, which means I do not have the ability to drink milk. Why? Well, I can drink milk, I just can't break it down, so it makes my stomach sore and very uncomfortable. How come? Because lactose is a sugar, but it is broken down by an enzyme called lactase. Because I inherited this gene, I do not have this enzyme that many of you do. So I am unable to break down lactose. Thus, I am lactose intolerant. Okay. So an enzyme is anything to be a substrate is anything an enzyme acts on. Okay. So substrates, where do they come in together? Okay. So we'll talk about that after. Let's just review this one more time. Okay. So first off, this is going to be you right here. All right. I love using the bicycle because everybody knows how it is, right? It's pretty easy. Okay. You're sitting here. This is your stored energy. Well, how do you know? Because right here it tells you this is your free energy, which means if you weren't up here, you would be down here somewhere, and that is 0, right? So you have some energy. The more up you are, the more you got. Now, you have to put in this much energy to get it activated, to get it started, right? Once you get it up here, once you put in that much energy, it's kind of like, you know, like that first pedal on the bike, you gotta kind of, and then after that you start going. That's what that activation energy is. And once it starts going, right, you just go, don't you? And now all of that energy is being released into the environment, and that is what you collect, okay? So this energy doesn't count, right? This is a wash. This is 0. You cannot count this energy. And a lot of people say, what are you talking about? This is a lot of energy. Well, think about it. If it cost you, let's just say it cost you 20 bucks, 20 energy, right? I'll just use dollars, it's easier, right? And this here is you get $20 back. You didn't really make anything, did you? Now, after that, you made $20 more. So what is your total change? 20 bucks. You can't count this 20 here because it costed you 20 to do it. So this is a wash. That's why I wanted to explain this picture before I did the other one. Okay, now, what does an enzyme do in all of this picture here? An enzyme will simply make this cost cheaper. That's all he does. He will reduce the cost to somewhere like this. Okay? So, for example, here. Now, normally you would go all the way up here, right? Remember, it's 20 bucks, $20 cash to get this done, 20 energy to do this, right? But you don't need to do this. You only got to spend, let's just say, 8, right? Instead of 20. I mean, you still got to spend something, and you get 8 back, right? Now, that's still better than putting in 20. Now, if you look at it in the form of energy instead of cash, that's a lot less energy you have to invest to wait to get back. So what does that mean? It means you do it faster. For example, I have this, and I have my phone, and pretend I have this red pen is more like a match. So I have to put in really, really hard 20 energy to get it lit, right? You ever had those really old matches and you're trying to light it and it just won't work? But then you get that new one. For some reason, there's something with it. You barely touch it, boom, whoosh, lights on fire. That's the difference what an enzyme does. It just makes whatever job you're trying to do easier, okay? And then it just helps you reach this point of getting the energy released that you need for your environment, okay? So I'm going to stop here because these, like I said, these videos are going to be a little longer than normal, okay? And then I'll make the next set of the protein video, and we're going to jump into induced fit as well as what happens when these proteins don't work right. All right, I will see you then. Have a good one.